We have already seen the primary batteries. Now we come to secondary batteries. Now as I told, secondary batteries, once their chemical reactions are over, you can recharge them by passing electric current, direct electric current through this cell, and the reactions will take place in a reversible way, and the chemicals are again stored there at the cathode and anode, and the reaction can be again started. So such cells are called, such batteries are called secondary batteries. So secondary batteries, once the reactions are over, we can recharge them. That is the main advantage of a secondary batteries. Now the main secondary battery we use is a lead storage battery. It is lead storage battery. You might have seen the lead storage battery in every vehicle. The lead storage battery is there. Lead storage battery, every vehicle has this battery. And what is the anode? The anode is lead plates. Lead plates are there as anode. And what is a cathode? Cathode is a grid of lead or spongy lead filled with lead dioxide, that is PbO2. So anode is grids of lead, pieces of lead will be is there as anode, and at the cathode we have the lead grids or lead spongy lead with lead dioxide PbO2 is filled inside. That is the cathode. And what is electrolyte? Electrolyte is a 38% solution of sulfuric acid. 38% solution of sulfuric acid is used as the electrolyte. Now the anode you have lead. Then lead is oxidized to lead sulfate. That is Pb. Lead is oxidized to lead sulfate at the anode. At the anode, Pb is oxidized to PbSO4. You know that the oxidation state, lead here 0, here it is +2. So lead is oxidized to PbSO4, and at the cathode what is happening? PbO2 is reduced to PbSO4. PbO2 is reduced to PbSO4. In PbO2, this is at the cathode, and PbO2, the oxidation state of lead is +4, and here it is +2. That means reduction. So at the cathode, lead dioxide is reduced to lead sulfate. So oxidation takes place at the anode and the reduction takes place at the cathode. So we get a supply. Now this is a lead storage cell. This is one anode, cathode, like this series it is connected. Each of them, these are 1 prime cells. They are connected in series to get a battery. So each one will give 1.5. Understood? Each one will give 1.5. This is one cathode, anode, then it is connected, then anode, cathode, etc. They are connected. And what they do is they connect from here to here. Then you will get the voltage. This is a lead storage cell. It is very old one. When this type of quality cells nowadays we are not getting. So this is a very old type of lead storage cell, and each one is 1.5. Suppose if you want a 3 volt cell, a single piece enough. 2 cells in series will give you 3 voltage. Understood? So this is what is a lead storage cell. Now next type of a secondary cell is nickel cadmium cell, and nickel cadmium cell, cadmium is the anode, Cd it is the anode, and NiOH thrice. This is here the reduction will take place, and Cd will be oxidized to CdO, cadmium oxide, and NiOH twice, nickel twice plus H2O. This is the overall cell reaction taking place. So cadmium it is oxidation state is 0. Here it is +2. So cadmium is oxidized to Cd2+. That is the oxidation taking place. Here nickel has an oxidation state of +3. Here it is only +2. So NiOH thrice is reduced to NiOH twice at the cathode. So this is a nickel cadmium cell. It is very compact, and one additional advantage is it has a very good voltage also, very compactly we can use. But another problem is it is very costly. It is not that economical. Nickel cadmium cells are very costly cells. Now we will come to another type of secondary cells. See, you know that in thermal power plants, actually what we do is we take energy by burning. Then this energy is released. What energy is released we will use for boiling water, and the steam is used to rotate the turbine, and electrical energy is produced. But there the energy that obtained from fuel is very less. The fuel efficiency is very less. Now they were thinking of converting the chemical energy of such fuels into electrical energy. And such type of cells where the chemical energy of the fuels is converted to electrical energy, we call such cells as fuel cells. One of the examples of fuels that can be used in fuel cell is hydrogen, then methanol, etc., ethanol, etc. can be used in fuel cells. The main type of fuel cell that was used is Bacon cells. Bacon cell, that is the cell used in Apollo space missions. There they use hydrogen oxygen fuel cell. That is, hydrogen was used as the fuel, and it is burned, or actually it is burned, and that chemical energy is converted to electrical energy. And the fuel efficiency is 70%. To 40%, 45% fuel efficiency we are getting in thermal power plant. Here we are getting a fuel efficiency of 70%. So the fuel efficiency can be increased by using such fuel cells. Okay. Now what are fuel cells? Fuel cells are, in fuel cells what we use is carbon electrodes, which are through which the hydrogen and oxygen will be bubbled through, and these electrodes will be filled with the platinum or palladium powder so that they act as catalyst in the reaction. So, and the electrolyte is sodium hydroxide or potassium hydroxide is used as the electrolyte. Now what is happening at the anode? At the anode, hydrogen is oxidized to water, and at the cathode what is happening? Oxygen is reduced to the oxide ion. So that is happening in cathode and anode. So at the anode, a cathode, O2 plus 2H2O gives 4OH minus. Here plus 4 electrons will give you 4OH minus. So oxygen, zero oxidation state, here it is -2. So oxygen is reduced to hydroxide ion, and at the anode, so this is the cathode reaction taking place, and the anode reaction taking place is H2 plus OH minus gives 4H2O plus 4 electrons. This is happening at the anode. What is happening? See, hydrogen, zero oxidation state. Here it is +1. So hydrogen is oxidized to water. Now what is the net reaction taking place? You see, the 4OH minus cancel. This will cancel. And see here 2. So the total reaction is O2 plus 2H2 gives 2H2O. See, this is the actual reaction taking place. So the one thing what they do is they do the converting the chemical energy of the fuel hydrogen is converted to the electrical energy. So we are getting 70% fuel efficiency. And another advantage of fuel cell is it is pollution free. It is pollution free. So these two advantages are there. It is fuel efficient and it is pollution free. See, in Apollo space transitions, The water produced they used for drinking purpose. The water was added to drinking water tanks and it was used for drinking purpose. The water used formed here. So it was an advantage for the space shuttle. Okay. So this is the fuel cell. This fuel cell which is a secondary cell. And you can continuously use this fuel. So this is a very cheap and very advantageable cell. So we will come to details. Lead storage cell. In the discharge state, both the positive and negative plates become lead 2 sulfate and the electrolyte loses much of its dissolved sulfuric acid and becomes primarily water. The discharge process is driven by the pronounced reduction in energy when 2H plus aqueous height of the acid reacts with O2 minus ions of the PbO2 to form OH bonds in water. See, this is a lead storage cell. You can see the positively charged, the anodes, you can see the anode is marked, then cathode you can see. Now, the anode is lead plates, they are lead plates, and cathode is the lead grills filled with the lead dioxide. Lead grills filled with the lead dioxide. Now, what is the anode reaction? In anode reaction, the Pb is oxidized to PbSO4. Pb plus SO4 2 minus will give you PbSO4 plus 2 electrons. And at the cathode, what is happening? PbO2 is reduced to PbSO4. This is what I said earlier. Lead is oxidized to lead sulfate at the anode, and at the cathode, lead dioxide is reduced to lead sulfate. And the overall reaction is PbS plus PbO2 plus 4H plus 2 SO4 2 minus gives PbSO4 plus 2H2O. So this is the overall cell reaction taking place. So a lead storage cell consists of the lead anode and lead dioxide as the cathode. The electrolyte is a 38% solution of sulfuric acid. Now next type is nickel cadmium cell. A nickel cadmium battery is a type of rechargeable battery using nickel oxide, hydroxide and metallic cadmium as electrodes. The nickel cadmium is derived from the chemical signals of nickel and cadmium. The abbreviation NICAD is a registered trademark of the SAFT Corporation. Now a fully recharged nickel cadmium cell contains a nickel oxide hydroxide positive electrode plate and a cadmium negative electrode plate. Then alkaline electrolyte, that is potassium hydroxide. See, this is the nickel cadmium cell. It is rechargeable. The cell potential is 1.30 volts and electrolyte nickel oxide hydroxide. So at the anode, cadmium is oxidized to cadmium Cd plus 2 state and nickel is reduced to, from plus 3 state it is reduced to plus 2 state. So this is nickel cadmium cell. Now next type is fuel cell. It's a type of galvanic cell that requires continuous supply of reactants. Fuel cells are not batteries because they are not self-sustained. We will have to supply the fuel. It is externally fed by the fuels like methane, then methanol, hydrogen, etc. Electrolyte is a hot aqueous potassium hydroxide solution, and this is the fuel cell. See, hydrogen and oxygen, they are fed into the porous carbon electrodes, and these carbon electrodes are filled with the platinum or palladium so that they act as the catalyst in the reaction. At the anode, what happens? Hydrogen is oxidized to water, and at the cathode, at the anode, hydrogen is oxidized to water, and the cathode, oxygen is reduced to hydroxide ion, and the overall reaction is 2H2 plus O2 gives 2H2O. That is hydrogen combines or burns in oxygen to form water, and it is highly pollution free and highly advantageous because they are nearly 70% fuel efficiency is obtained. So we have completed the two types of batteries. Now corrosion. What is corrosion? Corrosion is an oxidative deterioration of a metal. Actually, a metal is converted to unfavorable products. 25% of the steel produced goes to replace steel structures and products destroyed by corrosion. Rusting of iron requires the presence of both oxygen and water. Rusting results from tiny galvanic cells formed by droplets, water droplets. Now, we can explain the rusting of iron as an electrochemical process. Now, what is happening, we will see. Actually, for a electrochemical phenomenon, there should be an oxidation taking place, a reduction taking place, and the point where oxidation take place, we call it as a anode, and the point at which the reduction taking place, we call it as a cathode. So at any point of a metal, the iron Fe atom is oxidized to Fe2 plus. Fe is oxidized to Fe2 plus 2 electrons, and we call it as anode. And at the cathode, a series of reaction is actually taking place. The carbon dioxide present in the air dissolves in water to form carbonic acid. This carbonic acid dissociates to give hydrogen ions, and this hydrogen ions reduces oxygen to water. So the reduction is taking place there. Oxygen is reduced to water in presence of those hydrogen ions, and that point we call it as a cathode. So anode and cathode is there. So a cell is set up there, and this is the cathode reaction. Now Fe is oxidized. The overall reaction is 2Fe plus O2 plus 4H plus will give 2Fe2 plus H2O. And this iron 2 plus ions, they are oxidized to iron 3 plus, Fe3 plus, and they form the rest, that is Fe2O3 XH2. That is the water percentage of water varies. So it is, the rest is hydrated iron oxide Fe2O3. So we are explaining this rusting as an electrochemical process. At the anode, iron is oxidized to, or Fe is oxidized to Fe2 plus, and at the cathode, oxygen is reduced to water in presence of hydrogen ion. The hydrogen ions are obtained by the decomposition of carbonic acid, which is formed by the dissolution of carbon dioxide in water. And this Fe2 plus ions produced is oxidized to Fe3 plus in presence of atmospheric oxygen, and this Fe2O3 forms a hydrated compound called rust, that is Fe2O3 XH2O. That is hydrated iron oxide, which is called rust. Now how can we prevent corrosion? One is galvanizing. Galvanizing means we can coat the iron articles with a zinc. Zinc is melted, and in this molten zinc we dip iron articles. Since zinc is more reactive than iron, it easily oxidizes than iron, so zinc protects and reverses the oxidation of the iron. Now cathodic protection. It is the protection of metal from corrosion by connecting it to a metal, a sacrificial anode, or that like a magnesium or zinc, which is more easily oxidized. Then electroplating, we can convert cover the metal with another metal, that is electroplating. By applying paint or grease or rubber to prevent contact of metal surface from air. These are the methods to prevent corrosion. So we have seen the two different types of batteries, primary and secondary batteries. The secondary batteries we have seen is lead storage cell, which is the cell used in vehicles to start the vehicles. So this lead storage cell, it consists of a lead anode and lead dioxide cathode. Both are oxidized to lead sulfate, and when all reactions are over, you connect it to a DC current, and then the process is reversed. Lead will be deposited, lead and lead oxide will be deposited back, then you can again reuse that. So that is the lead storage cell. You can reuse again, recharge again. And another example is nickel cadmium cell, where cadmium is oxidized to cadmium oxide and nickel 3 plus is reduced to nickel 2 plus. So that is nickel cadmium cell, which is not that economical, it is a little costly one. So another type of very important secondary cell is fuel cell. In fuel cells, we are converting the chemical energy of the fuels, which is not trapped completely. That is the fuels, if they are burned in a thermal power plant, we are getting only 40% efficiency. If we are using such fuel cells, we can increase the efficiency up to 70%. So in fuel cells, what we use is carbon electrode, porous carbon electrodes, which are filled with the platinum or palladium as catalyst, and the electrolyte is an alkali, either potassium hydroxide or sodium hydroxide. Oxygen and hydrogen are bubbled through the electrodes, and at the cathode, oxygen is reduced to hydroxide ion, and at the anode, hydrogen is oxidized to water. In effect, or as a total, we can say hydrogen combines with oxygen to form water. And such type of Bacon cell is used in Apollo space transitions, and they trapped this water for drinking purpose. So this is a secondary cell. Now we can explain the corrosion or rusting as an using electrochemical theory. And corrosion is destroying almost 40% of the metal we are producing is destroyed by the corrosion. Now, how can we explain corrosion? See, corrosion we'll take the example of rusting. A point on the metal surface, that is iron, act as the anode, where iron is oxidized to Fe2 plus, and at the cathode, oxygen is reduced to water in presence of hydrogen ion, and as an overall reaction we have seen the Fe2 plus, and then it is oxidized to Fe3 plus by atmospheric oxygen, and it combines with the water molecules to form hydrated iron oxide, which is rust. That is the electrochemical theory of rusting, and we can prevent rusting by painting, by greasing, or we are with the cathodic protection. We can use more reactive metals to coat it, that is galvanization, etc. Or even alloying, forming alloys. We can make alloys using these metals, and we can prevent corrosion. And this is the electrochemical theory of rusting. Okay.